So we're now going to talk about when not to use Java parallel streams. There was a reality TV show maybe 15, 20 years ago called What Not to Wear. And it was these people who'd go around and tell people, mostly guys, probably mostly engineers who are guys, what not to wear, how not to dress to look sloppy or whatever, disheveled. So we're going to talk about when not to use parallel streams. So it turns out parallel streams are not suitable for everything. There's certain circumstances under which they should not be applied. So one example would be if the data source that we're trying to split either splits unevenly or splits inefficiently, or both. And we took a look at an example here in the EX14 case study that had the complete works of Shakespeare, and we split things up and did parallel stream stuff on this with both an array list and a linked list. So we would get all the words in Shakespeare, and we would put them into either an array list or into a linked list. And then we would discover, by timing the results, that linked list doesn't split evenly or efficiently compared with array list. And so when we ran the program, we found that the array list version was faster for what we were trying to do. Not much of a surprise, by the way. And when you look at the implementation of linked list versus array list, you can see that their split iterators are quite different, and splitting an array list takes constant time, and you end up with a nice even split every time. Split and no data copying. Splitting a linked list, in contrast, doesn't split evenly. You copy data, it doesn't split efficiently. It's just not nearly as good. So we get a nice speed up. Now, of course, your mileage will vary, and it has lots of things to do with processor speed and so on. But in a general sense, the more evenly and the more efficiently things split, the better. Here's just a quick illustration of this. You can see that the array list split iterator runs in constant time, and it does that because it can quickly figure out where the midpoint is in the existing list, and then it can go ahead and split things into two chunks evenly and efficiently, and no data copying occurs. In contrast, the linked list version is not nearly as efficient. It's not nearly as even. It runs in linear time as opposed to nicely in constant time here. And so as a result, it has more work. We have to create a fixed size chunk, and then we copy the data, so that's going to be inefficient. And then we pass it off to this helper method down below. And the consequence of this is it just doesn't work very well. Another situation in which parallel streams are not going to work is when the startup costs of parallelism are higher than the amount of data we can process in parallel. So when the startup cost is going to be high, then we have problems. And we talked about this earlier. Here's an example that illustrates this. We have parallel stream factorial and sequential stream factorial. And what's interesting about this particular example here is that for values of n that don't overflow for longs, remember long is a 64-bit quantity, but remember factorial grows very quickly. So if you get an n of around, I think it's 22 or 23, you quickly overflow the precision that you get with a long. And because of that, when we run these things in parallel, it actually turns out that the sequential version is most likely going to run faster than the parallel version because n doesn't get big enough to make up for the startup costs of splitting things up. Now, it turns out, again, if you run the EX16 example here, I also have this implemented with big integer, where I can give enormous factorials. So if you get n big enough and you have a data structure that will grow and be more and more precise the longer it runs, then you can get a win. But if n isn't very large and the overhead is larger than the benefit of parallelism, you don't get a benefit. So again, when n is small, not a good speed up. If n is small, the sequential solution will be faster. You can actually run it and see to prove it to yourself. Another situation under which things don't work very well is if combining partial results is costly. If it takes a long time to merge stuff together, then you've got a problem. Does anybody know where this is from? It's from, I went to India a couple years ago and took this picture. This is like India traffic. But actually, to be fair, when I went to the Nashville soccer club game last night, the traffic looked pretty much like this trying to get into the stadium. So it just goes to show that it's not just one place that has problems. But The most interesting thing, by the way, about being stuck in Indian traffic is, despite the fact that people are about a centimeter apart from each other, the amount of fender benders and accidents is remarkably low. And I think that's because Indian drivers have some kind of ESP or some kind of like mental brain sensor that keeps them from bumping into each other even though they're super close. This was an example we took a look at here for EX36, where we had the complete works of Shakespeare that we read in, and then we applied different kinds of collectors to it. And when we applied the non-concurrent collectors and we had to combine sets or maps, then it was expensive relative to applying the parallel collectors. So if we use concurrent collectors, I should say concurrent collectors, that optimizes the results. And you can see that we get better performance in some circumstances with concurrent collectors when running things in parallel. Another problem that we have is some stream operations don't sufficiently exploit parallelism. And the problem here is that certain things, while providing the right answers, take a long time to run. So this particular program, which is my EX15 example, will create a list that takes a look at it basically computes the square root of the first n even numbers. And this approach up here uses filter and limit and iterate with a parallel stream. And even though you get the right results, it's really slow. And that's because iterate and limit split and parallelize poorly because of the semantics of those operations. In contrast, you can compute the same results using the range method on long stream, and you can compute the first n even numbers, the square root of the first n even numbers, much more efficiently than you can do it this way. So that's another thing to consider. What are your operations? Obviously, if there are very few cores, if you have one core, you're probably not going to get a big win from streams. So that would be a problem. So make sure you have the right configuration. You know, most modern computers have lots of cores, but if you're running on a first generation iPhone or first generation Android phone or a Mac SE or something like that from 1986, not going to work so well. Another quirky thing about parallel streams is there's no built-in means to shut down the processing of a parallel stream. There's no operation that's like cancel the stream, which is kind of weird. But the best way to do this is to define some kind of volatile Boolean and then check that in all the methods that are being called in the parallel stream and throw exceptions if you're canceled. So you throw the cancellation exception. Not quite as transparent and invisible as we might want, but that's the approach we use for the image crawler stuff, the web crawler program that you guys have been using as the basis for your assignments. So I don't know if you've noticed this, but you can click on a little floating action button on the display and it'll shut down the parallel computations quite quickly, actually. So that's the end of a quick discussion of when not to use Java parallel streams.